All right, today we are going to be looking at what are called exponential functions. We're going to talk about the graphs of them, evaluating them, looking at what base E means, and then looking at some formulas that use exponential functions in order to solve. So we're going to go ahead and just start with what it means to be an exponential function. An exponential function is of the format of some positive number b raised to some x variable expression. And so what happens is your variable ends up in the exponent. So we've got a some number base example. It could look something like 5 raised to the x plus 2. So you see the variable happening in the exponent instead of the base. All right, so first example here is it says the exponential function given by 42.2 times 1.56 to the x models the average amount spent f of x in dollars at a shopping mall after x hours. What is the average amount spent to the nearest dollar after 3 hours at the shopping mall? And does this rounded function value underestimate or overestimate the amount shown in the graph? So it says, what is the average spent to the nearest dollar after 3 hours? And hours are our x value. And so what I would do is evaluate f of x for 3. So we get 42.2 times 1.56. And now I'm going to insert that 3 where there was an x. And so then I grab my calculator here. Let's see, calculator. Okay, and when I grab my calculator, let's type in that 42.2 times 1.56, and then we're going to have to get our arrow exponent key, and we said we were going to raise that to the third, and we hit enter, and it looks like 160.2, and we're supposed to round, I believe, to the nearest. To the nearest dollar, so 160. $160. So if we look at our graph here at 3 hours, it says that the average, let me zoom in there, was 149. And so I would say that our function is going to overestimate the amount spent by the data found. So when typing this in, we just have to find, a lot of your calculators are going to have this caret key. Some of them will have like a x to the y or a y to the x, one of those keys, but finding our exponent key in our calculator as we do that. All right, so then moving into graphing. So this is no longer going to be calculator based. We're going to be able to graph these by hand. But I just have some sample numbers for us to look at here. So we're going to use this sample function, f of x equals 2 to the x. If I plug in some of these exponents here, like a -3, let's take a second and look at that. So if we do -3, that would be 2 raised to the -3. And what we learned in algebra is if we've got a negative exponent, what I want to do is make this into a fraction and move that to the bottom to make it positive. And then I can actually do 2 to the third. 2 to the third is 1/8. And so we see that at -3, we'd have a dot at 1/8, which is way down here. And we could do that for each of these here. Similarly, if I was going to do 2 to the -2, it would drop to the bottom of my fraction, and 2 squared is 4, and I'd be looking at 1/4, which is also pretty low down here. Same thing with -1. I change that to a -1. And 2 to the first is just 2, so now we're looking at 1/2. And then I plug in a 0. So now things are going to change a little bit here. As I plug in a 0, we have to remember our algebra or our exponent rules that anything raised to the 0 is 1. And then you'll see that as one of the properties of our exponential is that we'll always have that point 0, 1, because it doesn't matter what our base is. When we raise it to the 0, we get 1. And now let's change this to the second. 2 squared is 4. Oops, I forgot one here. To the first. is 2. And you can see that my answers, there's 2 to the first, 2 to the second is going to be 4, 2 to the third. We start jumping up here very quickly, and all of a sudden I'm way up at 8. And if I raise 2 to the fourth, I get 16. It all of a sudden gets really, really big. And that's why it's called exponential. One of the things you'll notice is that no matter what smaller negative number I plug into this, I'm going to continue to get a smaller and smaller fraction. So it's going to get really close to 0, but never get to 0. And as I connect these dots, as I move to the right here, it just zooms up in the air, gets really big, really fast. All right, so we're going to look at, similarly, one with a fraction base, and look what that does. And we'll be able to fill this in kind of quickly as we start figuring out the rule here. But if we look at 1 over 2 and we start raising, let's look at this, is to the 1/3. That would be, each of those would get a -3 exponent. And again, to make them positive, we'd move them to the other part of the fraction. So that 2 to the third would move to the top, 1 to the third would move to the bottom, 2 to the third is 8, 1 to the third is 1. And so we see that when we raise 1/2 to the -3, I actually get a big answer of 8. -3, 8. And very similarly, we could go through and do this with all of those same exponents. So if we look at raising it to the -2, everything would get raised to the -2. Everything would move. 2 squared is 4. And same thing with -1. If I raise everything to the negative first, everything moves and is now raised to the positive first. 2 to the first is 2, over 1 is 2. And you can see that these same numbers seem to be repeating, and it is true because it's just the reciprocal of what we just saw. And then we start looking at those positive exponents. So when I start raising to the 0, anything raised to the 0 is 1. And again, we said when we have that exponential without our transformation, we'll always go through the point 0, 1. Anytime I raise something to the first, it's not going to change what I'm looking at. So 1/2 raised to the first is 1/2. And then when I square my 1/2, that's 1 squared over 2 squared. 1 squared is 1, 2 squared is 4. And similarly raised to the third. 1 cubed is 1, 2 cubed is 8. And we see that same graph, it just looks like it's reflected across our x-axis as we plug in bigger numbers. Again, it continues to be smaller and smaller fractions, but we'll never actually get to 0. So it'll just slide right along there. So that brings in a lot of our characteristics. First of all, there was no number I couldn't plug in. And so you see that we've got a domain that is unrestricted. It is 1-to-1 and has an inverse, and that we'll look at in a couple of days as we look at solving our equations that involve exponential and eventually logarithmic functions. And this is a big one right here. Huge, huge, huge. Understanding that, as I said, we could get really close to but never get to 0. That's our horizontal asymptote that we will be approaching without a transformation that runs right along your x-axis. And so it is very important that you understand that one of the characteristics of an exponential function is that it will have a horizontal asymptote of y = 0 when we don't have a transformation. Always a horizontal asymptote. And it will move with our transformations, and we'll look at that here in just a few minutes. So let's just talk just basics of transformations. As we remind ourselves of transformations, we always talked about things being inside and outside of our function. So what's inside and outside of an exponential function? Outside would be anything that you see multiplying in front, like this -3. So that would be like an ROX and a vertical stretch by 3. Anything added or subtracted, and then it could be actually in front or behind, and anything added or subtracted would be like our ROX or ROY. And then anything that would be considered inside has to literally be written up in the exponent. And so that would be all of your ROYs, your horizontal strength stretches, and your movements right and left would all be written inside the exponent. Now, one thing I did not talk about was the number 5 And people want to call that a transformation. That's actually our base, and that will give us our set of parent function or our set of parent points or our favorite points to start graphing that we're going to transform. But it is not actually a transformation. It's just the base of the function. So like the base of this function would have been 5 raised to the x, where the -3, the negative x plus 2, and the -4 would all have been then considered transformations of the function 5 raised to the x. So if we then look at what that would have looked like on our cheat sheet for transformations, if you remember, the first thing we address is negatives. What do those look like in exponential functions? In an exponential function, it would be sitting in front of our number to look like an ROX. And just a reminder, that means that in our table of favorite points, we will go down our Y column and switch all the signs. And in an exponential function, an ROY will look like a negative that is inside the exponent, and that would go down our X column and switch all the signs. Vertical and horizontal shrinks and stretches, again, multiplication, and where are those going to appear? Vertical shrinks and stretches are going to appear in front of our number. Vertical, remember, will impact our Y column by the number that is there. So if it's a 3, we would multiply by 3. Horizontal shrinks and stretches will show up in our exponent. Horizontal inside our function will impact our X column. So if it's a 3, remember inside things will impact our X's by the reciprocal. So I would have in this example multiplied by 1/3 down the X column. And then thinking about our ill route for our shifts right and left, up and down. If it's inside our function, it will move us right or left. And at this point, remember, I'm just counting on my graph. So if I see this x plus 1 in our exponent, that plus 1 would move our graph, again, opposite for inside, so left 1. And then if that plus 1 was not in the exponent, that would be outside our function, and we would consider that moving it up 1. And then this is a very, very important point right here, and that is that any movement up or down will also move your asymptote that same distance. So if we say that our graph is going to move up or down, we are going to draw our asymptote moved up or down, because that will be part of our graph as we draw that as well. So now we're just going to see these in play, and the first thing that we'll need to look at is how do we come up with our favorite points for this graph. So because they all behave very similarly, what we're going to look at is, it says use the graph of f of x equals 3 to the x, that's your parent function, to obtain the graph of g of x equals 3 raised to the x plus 1. And so what we do is we use this function, f of x equals 3 to the x, or more importantly, the 3 that is in there, to build our set of favorite points. Okay, now typically, and once you get really good at this, I would go just from -1 to 1, but in the meantime, if you want to go from -2 to 2, you can do that. And we're just plugging these points in. We already should know the shape of this graph. And so these again are just of our 3 to the x without transformations. So 3 raised to the -1 is going to move that 3 down to the bottom, raise it to the first, which would just be 1/3. And then if we raise it to the 0, anything raised to the 0 is going to give us 1, and 3 raised to the first is going to give us 3. And what you'll notice is anytime we raise it to the -1, we will get the reciprocal of our base. When we raise it to the 0, we will always get 1, and when we raise it to the 1, we will always get whatever our base is. That's never going to change on our exponential functions. So then applying our transformation, they ask us to graph g of x equals 3 to the x plus 1. Let me zoom in on that a little bit. And so I just decide what is the transformation that involves a plus 1. And so that plus 1 is inside my function, inside addition, means I'm going to move each of those points left 1. If I'm just going to move them left 1, what I would do is lightly dot out the points that I have, which would be -1, 1/3, 0, 1, and 1, 3. And then I'm going to move them each left 1 to actually get the graph here. And then what I ask myself is, did I move my graph up or down? I did not. And so because I did not move my graph up or down, that horizontal asymptote will still run at my x-axis, and we will not move that from our x-axis, which is the line y equals 0. We will not move that horizontal asymptote until we have a graph that moves up or down. And so now I'm just going to slide along that asymptote, shoot through my points here, and continue to get really big really fast. Your domain, you will never have to think about this on your exponential. It always will go from negative infinity to infinity. Our range we get really close to, but we never actually get to, so parentheses, 0. And then it goes up forever, so infinity. And our asymptote did not move on this one, and that is at y equals 0. And what I want to point out is, if I can really zoom in on this, your range and your asymptote will match. Whatever number we have for our asymptote will match either the first or the second number in your range, because your range will go up to that asymptote. So if our graph happens to get flipped, it might match the second number, but it will match one of the numbers in your range. All right, let's look at some more examples of that. So again, we're going to start with just that parent function to build our table of favorite points. We now know that our favorite points are always going to go from -1 to 1, that when I plug -1 in, I get the reciprocal of the base. My base is 2, so 2 raised to the -1 is 1/2. 2 raised to the 0 is 1, and 2 raised to the first is 2. And those would be my initial points to start with. And then doing our transformation. So on this one, we can see that our transformation is an outside subtraction. Outside subtraction means we are going to move down, and that is a key word on exponential, down 3. When we move up or down, that means our asymptote is also going to move that same direction. So asymptote 2. So what you'll notice is the first thing I do is I just move that asymptote down 3. So it will go down here. It was at 0. Now it is down 3 at y equals -3. Go now take each of your points. We're just counting. So I'm going to take each of my points and count down 3. So 1/2, down 1, 2, 3. From up 1, down 1, 2, 3. Down 1, 2, 3. We get that same shape that's going to slide along my asymptote, go through my points, and then get really big really fast. Your domain will never be restricted, so from -infinity to infinity, but our range is different this time. It moved down, so the lowest point we're going to get close to is -3, but still go up forever. And again, remember that range and your asymptote should match. All right, now let's look at one that has a fraction base. So our fraction base is the 1/3. And again, that is just used to create our table of favorite points. Your favorite points, so remember that when we raise it to the -1 is the reciprocal of the base. Well, if our base is 1/3, its reciprocal is 3. Raising 1/3 to the 0, anything raised to the 0 is 1. Anything raised to the first, we keep the same. So we get that 1/3 or whatever our base was. And so this is the one that will decrease as we go. So then looking at our transformation here, we've got a negative on the outside. So I'm going to zoom in on that. Let's erase that and zoom in. That negative on the outside, let's address that first. That's an ROX. So I'm going to come to my Y column, and I'm going to go down that Y column and change all the signs on my numbers. Then the next thing I want to look at here is we've got a 2 in front, and that's a vertical stretch by 2, and vertical stretches by 2 multiply our Y column. So I'm going to go down my Y column and multiply by 2. And that's it for our transformations. So again, I asked myself the question, did we have a transformation that moved our graph up or down? And because we did not, that means my asymptote does not move. It's going to remain at y equals 0. But we did have transformations that did move us a little bit here. And so now I'm going to just go graph these points. I've got the point, let's see, a -1, -6. 0, -2, and 1, -2/3. And so what happened is my graph got flipped over our x-axis, that ROX, and so now it's underneath my graph, and it's going to head towards that asymptote and slide along my asymptote. Again, my domain will never be restricted, but our range this time we have to slow down a little bit. Our lowest point is actually going to be -infinity. Our highest point is it's going to head towards that asymptote. So you'll notice again, if I zoom in on that, my asymptote and my range do have a number that matches, right? This time it just happens to be the second number in my range because it will always head towards that asymptote. All right, next we're going to get introduced to this thing called the natural base, or the letter E. E is actually a number. You'll see right here that it is a limit. We know limits, and it says as x approaches infinity of that equation, x plus 1 over 1 plus 1 over x raised to the x as x goes to infinity gives you this number. And this number is similar to pi. I only have it written out to 3 decimal places, but we can put ... here because it actually never ends. It never repeats. It's what's called an irrational number. Like I said, similar to pi, that goes on forever, never repeats, never ends. And what E does is it actually ends up explaining real life exponential growth a lot better than any other number can. And so you see things in exponential in terms of E quite often. So how do we graph E? Here's what you need to know. If we go back to our idea that this is our reciprocal, and this is our base, but I don't know what E is. I'm going to graph, go back to this right here, 2.7 approximately. When my base is E, anything raised to the 0 is 1. And then if you grabbed your calculator and you typed in, there is an E button. If you look, there's actually 2 E buttons. There's an E, and then you can raise it to like an exponent. There's also an E button. Now, let me see if I can grab my calculator here. An E button that is down the left-hand side where it says mine is the, let's see, third button up, natural log button. If you look at the top of that, it says an E to the X. I have to use my second key to get that. But if I hit my second key and I get my E to the X and I raise it to the -1, you can see that it gives us approximately 0.367, or approximately, we'll call it 0.4. And here's my note to you: memorize. Memorize that number, memorize that number, because you will not get a calculator for this. You have to just know those 2 numbers. And so what do those look like then on our graph? Very similar to what we saw before. So -1, 0.4, 0, 1, and then 1, 2.7. It's going to slide along that horizontal asymptote at y = 0, and then get really big really fast. It also does not have a transformation, so horizontal asymptote at y = 0, just like any other exponential function. All right, so let's practice graphing one of those. Again, we start with just the basic parent function. We just set this up on the last page, and we know that the reciprocal we are going to memorize is 0.4. Anything raised to the 0 is 1, and E is approximately 2.7. Let's apply some transformations to this. I'm going to zoom in a little bit because it's kind of hard to see here. There is a negative right there in front of the X, and that is an ROY. ROYs go down our X column and change the sign on everything. So that's the first thing I would do on this problem. And then it's got a -1. And remember, minuses and pluses outside, that's going to move us down 1, which is also our asymptote 2, right? So the first thing we're going to do is move our asymptote down 1. Oops, that's down 2. I'm numbered by 2s here. Let me go down 1. So my asymptote moved down to y = -1. And then I have already applied all my transformations by going through the X column and changing the sign. So now I can just graph these points, +1, 0.4, and then I need to, so that would be here-ish, and I need to move it down 1, And then 0, 1 would be here, move down 1 would go through 0, 0. And then negative 1, 2.7 would be about here, move down 1 would be at about 1.7. And so let me get rid of those other dots. Those are the originals. I moved all of them down 1. And our graph would look something like that. Like every other exponential graph, your domain will never be restricted, negative infinity to infinity. Our range, again, will match our asymptote. So the lowest point on this is going to get close to, but never get to negative 1, and it will go up forever. All right, I think we've got one more example here of a transformation using our exponential. And again, one more example of our base of e to the x. So exponential, we're going to go from negative 1 to 1. The reciprocal of e to the x is going to be 0.4. Anything raised to the 0 is 1. E is 2.7. And let's look at our transformation here. It is a 3 on the inside, which is a horizontal shrink by 1/3. Horizontal, we always have to think opposite. Horizontal things impact my x column, so I'm going to multiply my x column by 1/3. That is the only transformation going on here. So then we would graph those points on our graph. So negative 1/3, 0.4, would be somewhere way down in here, 0, 1, and then 1/3, 2.7. Squished my graph really close together. I did not say the words up or down, so my horizontal asymptote is not moving anywhere. Still at y equals 0. It's going to slide along that asymptote, go through my points and get really big really fast. Your domain is never restricted, and our range will be getting close to 0 and then up forever. All right. The last part of this section then is covering functions that are, or formulas that are created by exponential functions. So like on this one, we've got our compound interest formula. And this is a point, especially in this video, where you might want to pause the video and kind of write down each of these things that you're seeing here. But what this does is it will find an accumulated value, a lot of times for like a bank account or interest earned of some sort. And your answer is that accumulated value. P stands for what you initially started with, principal, the beginning amount. Inside you see it's 1 plus. Your rate is your annual percentage rate is a decimal. So for example, if they were to have something like a 2.7%, that would be a rate of, and to move from a decimal to from a percent to a decimal, you will take that decimal and go 1, 2 spots or divide by 100. So R in the formula then would become 0.027. N represents the number of times that you are compounding your interest per year, and T represents how many years you leave your money in this account or are accumulating interest. I do want to talk about N for just a second. N represents the number of times you compound per year, but a lot of times they'll give that to you as words. And so these are the words that you want to be able to recognize. If they use the word semi-annual, that means you would be putting in an N value of 2. If they give you a number of times as quarterly, you'd be putting in an N value of 4. Monthly means N equals 12, and daily is N equals 365. Now, there is a second formula that is used to find interest, and that is what's called, we refer to as your PERT formula, if you can kind of see that word PERT showing up in there. And that is all based off of the word continuous or continuously. So when they say that something is being compounded continuously, not quarterly, not semi-annually, not monthly, they use the word continuous or continuously. We flip to this different formula called PERT. We still have that accumulated value at the beginning, our principal, but now notice we use E as our base of our exponential. Our rate moves up into the exponent still as a decimal, and then we just multiply it by the number of years. So looking at these side by side, and this is a little bit of a calculator thing, so we might need to spend a little time here making sure you can type this into your calculator and match my answers. But it says you decide to invest $8,000. So decide to invest $8,000 means that's going to be your principal amount right there for 6 years, and that's going to be your time. You have a choice between 2 different accounts that you can put this in. The first one, which we'll call option 1. So on option 1, it pays 7% annual percentage, and it's compounded monthly. So interpreting what those 2 words are telling us, that means 7%, our rate, so let's take our decimal point and move it 2 spots, will be 0.07. Compounded monthly means our end value is going to be 12. So when we set that up, it's going to look like principal is 8,000, 1 plus our rate, 0.07. N shows up twice in this formula, once in the bottom of the fraction and 1 time in your exponent. And then your exponent is also then multiplied by the number of years that we are leaving that in there. Oops, not E. We are leaving that in there for 6 years. So if I go type that into my calculator here, let's see if I can get all that, 8,000. So I would start with 8,000 times 1 plus, and some of you will have an option here, and I don't think I do, so I'm going to have to make mine into a fraction by doing divide 0.07 divided by 12. Some of you are able to type in the fraction. Now notice I had to put mine in parentheses, so I'm going to put a double parentheses here to close that. And then I'm going to use my exponent here, and we are putting in a 12 again times 6 years. And it looks like we get 12,160.84. And we'll compare that then to what we get for option 2. So let's look at option 2. Option 2 switches up a little bit. We get an interest rate of 0.685, and it says continuously. So those 2 things translate into a rate of, again, moved by decimal 2 spots, 0.0685, and compounded continuously means our base becomes E, or we use the PERT formula. So that setup would look like our accumulated value will equal 8,000 times E raised to the 0.0685 times 6 years. So let's go type that in our calculator. $8,000, and I'm going to get that E raised to the, and our interest rate was 0.0685, again for 6 years, and we get 12,066.60. And we just compare those 2 values, and it looks like our one that's going to earn us a little bit more money on this would be option 1. So what I would encourage you to do is make sure that you can type in the 2 formulas that we are seeing here and here. All calculators are a little different, but make sure you can type those into your calculator and get the values that I was getting. And if you are getting those, then you are typing them in correctly and you should be good to go. Your assignment is a worksheet.